So recall, this is the kind of thing we're interested in. We're interested in this maybe averaged over time, right? All right. This is equal to the expectation of C of xt ut given my observations. This is a hint. We'll get to it. All right? Now, I'm going to stick to a finite state space. So, ut is already in yt. So my ut is a function of present and past observations. So that is basically a given this. And so really the only randomness, the only uncertainty is xt. Now don't worry, we haven't done much. So I said recall the smoothing property. We're interested in average cost, expected cost at time t, the expectation of the conditional expectation.
Is that the law of iterative?
I guess it's called that too. It's also called the smoothing property. Yeah.
Is it also called the tower property?
Yeah, I've heard the tower property. Yeah. But I think, well, anyway, yeah, in my world, smoothing property is the most commonly used. But yeah. So. We're going to take a finite state space, sort of countable, but no, finite, forget it. And so this is really, all I need to know is the conditional probability mass function. The conditional probability that x equals x given yt for every x. And then I can just write this down. I mean, not expectation. Oh yeah, I need the expectation. The thing inside is a summation over x of this probability. Okay. So the thing inside this expectation is this. That's not really, I mean, it's not really random. Given yt, because ut is a function of observations up to time t. That guy is, you know, I mean, it's random only. I mean, it's, sorry, excuse me, what was I trying to say? Back up again. These guys are both random. They're both random. Forget it. I was just able to ignore it when I did this. I was able to treat that as just a constant. But what you see is this. I had an expectation of a nonlinear function of x and u. And what I've left up with is an expectation of something that's nonlinear in u, but a linear function of b. All right? So every cost function is linear in what's called the belief state. And so computer scientists are incredible at marketing, you know? And from data, they derive knowledge through belief states. It's really, I mean, but anyway, you'll see this language. Yep. I'm trying to explain.
Oh, okay.
I'm just going through this slowly. I'm revealing this to you. You know, there's two important facts. One is that I've converted my expectation, you know, of the cost of xt and ut. I'm not observing xt. I now have as an expectation of ut, a function of ut in this belief state, where ut and bt are both things I observe. I'm observing bt. It's derived from this nonlinear filter. It's by definition, it's a function of the y's. Okay.
So,
Well, hold on, you first.
We're going to see that somehow that first expectation is not deterministic.
Oh, no, it's random. I just made a little mistake. I was just want to emphasize that I could treat that as deterministic, take it as conditional expectation, and I basically just looked at the conditional probability that x equals x and multiplied by c of x ut and summed over all x's.
I thought
Just
it was a rule that the output of an expectation is deterministic.
Conditional expectation is random. This is the thing inside.
Okay.
The conditional expectation is a function, given yt is a function of y0 up to yt. All right? Okay. So we're getting there. So so our objective now. So what I'm going to do is this. God, there's so much in these notes, but I don't think we have time to go through it all. Yes, I'm not going to do it. What I'm going to do is this, then. What we're going to do is, so here are the conclusions. So the first thing is that I'm just restating what I just said. If I average both sides of the equation, I get to the average cost that I cared about before is now an average cost where I've got a function of the belief state in the input. All right. And two, unfortunately, it doesn't work for BT, but if I take something a little bit bigger, I'm going to denote IT as BT and YT together, the pair process. So BT is a probability mass function, random, that's evolving in time, if I'm there. And then YT was the observation at time t. That we're going to call the information state. So we've got a belief state and an information state. And from this knowledge, we will gain wisdom. I should be careful. I should be careful, because language like that really is used in this world. But it's called the information state. There is some good statistical reason for this. It's just the pretension around this is crazy. What's awesome about this is it's a controlled Markov chain.
that is.
And it's almost obvious that it's a controlled Markov chain. It's so fucking, awesome. That the probability that, I know that, so BT is a vector, and Y is going to list in a finite alphabet. But if I look at the probability that IT is in some set S, I mean, of course, a set S would be a product. I just will write this abstractly first. Given I0 up to IT, that turns out to be equal to something much bigger. So there might be some loss of, no, it's the same, I'm sorry. Excuse me. If I observe the ITs up to time t, It's exactly the same amount of information. I'm sorry, this is equality, obviously. The same amount of information here and here. But by writing it this way, it turns out to be trivial. You can, oh, but minus one. It turns out it's trivial to show that you only need the last guy. The last guy, but it's a controlled Markov chain. And who likes Bayes rule? Over there likes Bayes rule. It's Bayes rule. it's completely nothing. Isn't that awesome?
So you're saying if we extend the observations with the belief as like an extended observation, then the evolution of that is a Markov.
With a completely observed Markov chain. I told you I observed YT, and BT is a conditional distribution, so I'm generating that at a computer. But through repeated applications of Bayes rule. So that's the thing. In stochastic methods, we derive this. You can go to Wikipedia and look up the filter. It's a trivial recursion. I'm not going to derive it for you. You can, But when you look at the recursion, you see right away that this thing is from the filter. You get this from the definition of the filter. I've got notes which I will give to you so you can see the derivation, and I'll give you references. But
so BT is not like something we know in general.
We do that. We derive there's a filter. There's a nonlinear filter, and when I taught this course last, I actually derived it, and pass that back. But yeah, I'll send you the derivation. But you can go on Wikipedia. You can go Bruce Hayek's course notes or any textbook on stochastic methods. They'll give you the nonlinear filter. It's a very simple update rule. So given those two primitives I gave you, that Q of y given x, and the controlled transition matrix, there's a simple recursion. It's almost linear. If you don't normalize it to be a probably mass function, if you don't scale it, it's a linear filter. BT plus 1 is a random matrix times the previous BT, and you have to rescale. I'm not gonna. There's no point in doing that. But what's beautiful is from that you get this wonderful fact. So it's over, And not only that, the fact that the cost function is always linear in the belief state. What you find out is that there's a value function, right? Remember there's an 8th star? That's an 8th star of B. So before it was a function on states, now it's a function on vectors, on probability mass functions. But it's always concave. And so the proof of that is exactly the same as the proof of concavity of those things that I talked about before. The minimum of linear functions is concave. The fact is, for a fixed policy, right, look at here, that's a linear function of beta, of B. And it comes from that. It's always concave. So that structure, maybe it'll help for approximations.
I have a couple questions.
Yeah.
First of all, you were saying IT is an A.
Oh, not B. It's concave in beta. That's right. So 1 second. It's the information state. So in the first variable, it's concave. Yeah. So yep.
Is S any special setting here? Or
Oh no, all S. No, sorry, all S. No, I'm just saying that I'm talking about predictions. So this is how you define the Markov property. I say for any set, what's the probability that see, T takes on continuous values because BT is a random vector.
So S is just any set.
Yeah, that's right. All possible. Yeah.
Okay, so my next question is.
For example, S could be, it could be the probability that BT is in some interval and Y is equal to some particular Y.
That's fine. I noticed that you have YT minus 1 at some point, which is a sigma algebra that defines the T minus 1 and you're conditioning that. And then you're substituting that for IT minus 1, comma UT minus
No,
1.
no, look, then take a look at the definition of IT. If you told me all the i's, I0, I1, I2, up to time t, well, then I'd see all the y's.
Yeah,
you know.
I can see
So
going from here to
these are the
here.
same, yeah.
Now, where I'm having a little bit of trouble, I can see how UT minus 1 will be in YT minus 1.
Yeah.
Now, IT minus 1, so what is troubling me about that is, have we proven that BT lies in YT?
Oh, no, it's a definition. Take a look.
Yeah, it's a probability condition of that.
That's the definition. No, yeah, definition of conditional probability is, it was our minimum mean square estimate definition. So conditional probability is a conditional expectation. So,
Okay.
yeah,
Uh-huh.
yeah. It's a conditional mean of the indicator function, you know. The random variable that's 1 if this is true in zeros. So, yeah. Yeah, that's what I meant. You can't, the conditional mean of x is absurd. It doesn't mean anything in this context. You need this whole monster. You need this belief state. You know, yeah.
To me about us
Yeah.
like using the BT is that like if we had that the probability of like the state being a certain state given the measurements, we could just evaluate that at the measurements that we got so far and just pick the x that is you do a math.
Well, that's a maximum likelihood estimate.
But
That's
you before said the reason we don't do that is because that p of x
Oh, no, it's-
y is not available to us. Now it is for some reason.
No. These are different approaches. So we could cut a maximum likelihood estimator for x, but what would you do with it?
I mean, I would just let that be the state estimate.
That's another ad hoc trick people use. You know, so instead of the conditional mean, you can look at the maximum likelihood estimate. Actually, Joel asked, so you could talk about ML estimate. So I could take my estimate of xt as the guy with maximum probability.
Yeah. If we,
And what would I do with that?
this b sub t.
But what would I do with it? I mean, that'd be another hack. You could try that, but it would not be optimal. And
So now that we have this Markov process for information, I guess you haven't said it yet, how do I then choose my state from it?
What's that? Oh no, I didn't give you the equations because you can see why. Take a look at that page. That's not for you to keep because it's got some mistakes I have to correct, but I'll send that out to you. But it's some tedious equation. So there's a nonlinear recursion. You know, it turns out that you can show that. It turns out, BT is some crazy function of BT minus 1, YT minus 1. Oh, I missed it. There should be uppercase. And the F is really a big, complicated mess of sums and inverses and normalizations and all sorts of crazy things. But the new vector is some function of the old. And once you get this, you can prove this in one line. And I was tempted to do it. And it's just, I don't think it's worth it. Maybe it is. I could if you want me to. But this representation, given the structure of Y, implies this. And if you want me to, I'll give you a proof right now. that this implies this implies that equality. I don't think it's worth it. I don't know. But again, just ask. Yeah.
Can you repeat one more time? A little while ago, you gave a nice little sentence explanation of that last result, number 2 there.
Number 2. I mean,
Say that in words again. That 3 equality.
No. The fact that these are equal is obvious because IT, for each t, IT has more information than YT. But if you look at the whole bulk, if you look at everything from 0 to t minus 1, it's the same information as the y's from 0 to t minus 1. So this equality is obvious. This equality is not, and you have to play around with the fact that the nonlinear filter has this form, that the update equation getting BT is a function of YT. And that's why I have to put in both. It's that damn tail thing here, that yt minus 1, is why I've got to put both of these guys in to get a controlled Markov model. Yeah. A lot of people forget that, by the way.
So
Yeah.
what that's saying is like the probability that your information state lies on a set only depends on the control action that was taken in the previous step and the information of that previous step.
Well, no, it's just, again, it's the memoryless property, right? And it's for both. So
Yeah, it has a memory.
yeah, that's all, yeah. So if I want to predict the future of this process, given the entire history, I only need the current guy. And, yeah. And then the other term for this is a sufficient statistic. See, we're trying to do some data reduction. We don't want to collect more and more data. You know, we want to somehow have a finite amount of data to store at each iteration. And so IT is a sufficient statistic. For this problem. I mean, you can make that precise, but I won't. I mean, so you can see how stuck you are. I mean, I went through and I gave you all this theory for controlled Markov chains with a finite state space. Suddenly we have to go to, if they're D states, this is an RD. You know, you think you're going to use value iteration for this? I mean, it's you know, it's an uncountably infinite number of states that B can take on. And so nobody has solved one of these problems practically.
BT would be between 0 and 1, right?
No, it's a vector. It's for every x.
I know, but
Yeah. So there might be 100 states, so it's a vector in R100. So, or something. Well, like in your problem, x is 3-dimensional, so it's in R3. So I've got y maybe takes on my observations. Well, I am going to give you homework on this. Like you have partial observations when the guy's on the hill. Okay, and so basically y takes on two values: 0 if you're at the bottom of the hill, middle, or if I got unlucky, didn't see you on the top of the hill. 1 if I happen to see you on the top of the hill. So y takes on two values. B takes on infinite dimensions because it's probability mass functions on those 3 states. So this is a vector in R3. Yeah, and so remember when you applied value iteration, you needed a finite state space. Yeah. So what we're saved. I mean, people do hacks and use the fact that this is concave, and so they do approximation methods. So it's a very immature field. I don't know of any work I respect. Yeah, I might have missed it, but I haven't seen any papers that I like about trying to approximate this guy. You know, it's sort of a fertile place to play around. But once you have an approximation, you're done, because we've got this control transition matrix, which I haven't written down. Is very simple, you know, and once somebody tells you this thing, then you've got your policy, you know. And we will learn about ways to approximate. And I wish I'd covered the homework problem you could do. I mean, so you guys have to do reports. I hope one of you actually messes around. You can find papers where people hacked away at approximating this monster using the fact that it's concave, you know. And so what do? You take a bunch of functions and pick the minimum. That's how you get a concave function, you know. And you know, and then you basically move them around and try to get the best performance. You get a family of approximate value functions, and you can go in and try to tune them. You know. You know. But that's the fluffiest. Every time I've taught this course, I've never been this fluffy, but I think it's good. I mean, you know, this 2 things is really all that's important conceptually. The rest is horrendous calculation. Like deriving this transition matrix from this even takes 20 minutes of scribbles. I don't know if it's worth it. Is it worth it?
It's in the notes.
Yeah, I don't think it's worth it. It's it involves this transition matrix involved those two things I mentioned before, that transition, that probability, that Q of y given x and all that. But it's not a big deal. I'm sure there's something else I wanted to say. Yeah, so the notes also, I make it much clearer what I mean by this. There's a lot more statistical mumbo-jumbo in here which you don't need to know. Over here, I did make notes to myself on this derivation, and I will give it to you in the notes for you to look at. So there's what can I kill? At some point, there's the LQG problem. You know, it's amazing we've gotten to this point and we haven't talked about LQG. Yep.
Can I ask one more question before we move on?
Yeah.
Can we just touch on, can you comment on why those two average costs are equal again?
The smoothing part, what do you mean? No, look, right there.
Oh, okay.
That's right there.
Follows from now.
Yeah, and then all I did is I averaged both sides of it to you.
Okay.
Yeah, okay. Okay. Yeah. So remember when we did Poisson's equation for the linear model, statistics were irrelevant. Well, it turns out, we haven't shown this yet, but for the fully observed case, the same thing is true. Statistics are irrelevant. The optimal control solution is the same as if there was no noise. You know, I didn't show it to you, we'll see that. And you don't need to be Gaussian. It just needs to be ID and zero mean. Nothing matters about statistics, nothing. For the fully observed case, the only reason they put that G in for Gaussian is that in order to handle this situation, you need Gaussian, because in the Gaussian case, this becomes finite dimensional. BT only depends on the conditional mean and conditional covariance. You know, so BT is finite dimensional. And H is quadratic in its variables, and we'll explain what we mean by that. We'll have to take the belief state and write a different representation for it. But it's just what a lot of you have seen before, I think. Yeah. So that's the only problem we can solve. All right, and then you can talk about hacks, heuristics that people come up with. One of them that's beautiful is bandit problem. And there's a million different variants of this, But one of them is where the state, nothing changes. Xt plus 1 equals xt, sort of, and your actions are pulling arms on a slot machine, and you want to make the most money you can, all right? And so there's this, the reason that people talk about it in classes is because it's a nice example of this fight between greediness and learning. Once you make some money, you want to keep pulling that arm, but maybe the other arm you'd make more money. And so, you can imagine what you do is you keep a tally of how much money I've made in this arm or that arm, and you start to slowly forget the arm that doesn't seem to be paying off. Well, there's certain cases where it's completely solved. They're hacks. Nobody knows what the exact optimal solution is to that problem. Nobody knows. But you can come up with heuristics and tune them so that they're really almost optimal. And so you get heuristics here. But again, the heuristics have a general enough flavor you can apply them in other settings. So I'm not going to spend a lot of time on that, but I'll give you the main ideas, some really pretty work. And I was joking, I think I might make Anand do this. I don't know, we'll see. But the third thing is that, damn, I wish we could, someday somebody's going to make an elegant theory. It's so frustrating here. I'll put a star there. You know, given that it's a concave function of B and all that, you know, it looks like this. There's some structure there. You know, there must be some way of getting intuition about what this looks like. Like if I know, if I understand the fully observed problem, how does that help me get guidance on it, on what this looks like? And that's sort of empty. I don't know any results, you know. But at least if you find some intuition, you know, we'll get tools for finding this. What I mean by this is you have some parameterized class of approximating functions, and you want to find the theta star so these guys are approximately equal. And that's all the Q-learning stuff and reinforcement learning. So you see it's learning. You know, it's like I say. And that's the course. I guess that's, you know, that's, yeah. And for that you need stochastic approximation more than anything. The only big mathematical tool is right there. Because here, the mathematics are beautiful, way beyond the course. It's all information theory. Yeah. And this is, the mathematics is nothing. You know, so it's only, that's the only big math sledgehammer we're going to need to talk about. All right. See you at the bars in 6 hours or so. Oh, that's right.